We have already encountered the issue of alkene stability when we talked about Zaitsev's rule, which stated that more stable alkenes, which are more substituted ones, form larger amounts during E1 and E2 reactions. Today we will look at the comparison of methods for determining the stability of alkenes, and we'll look at how the stability of individual alkenes compare among themselves. We have already seen one method based on heats of combustion, which is used for determining the stabilities of organic compounds, chiefly cycloalkanes. In this method, we compare an unstable compound and a stable one, and upon combustion, both of these compounds are converted to the same amount of CO2 and H2O. They're converted into the same amount of CO2 and H2O because they're typically either isomers or they're benchmarked to per CH2 group so that they give us the same products upon combustion. The unstable compound would have the higher delta H combustion, while the more stable compound would have the lower delta H combustion. So it would be a small value, whereas this would be a large one. With alkenes, we can apply the same system just fine. However, typically this is not done. Instead, what is used is an alternative method based on heat of hydrogenation. And hydrogenation is a reaction that any alkene would undergo, where the double bond is treated with hydrogen in the presence of platinum catalyst to give us a saturated compound. And this reaction releases a certain amount of heat. Now when we compare two alkene isomers, they both get us the same ground state, that is alkane, because they're isomers. But the unstable one will release a higher amount of energy upon hydrogenation, while the more stable one will release the lower amount of energy upon hydrogenation. Okay? In our comparison of these two numbers will allow us to determine the difference in their stabilities. You might ask, well, what is the difference between these two methods? They seem to be operating on the same principle, and you're correct. The fundamental principle behind the operation of these two methods is exactly the same. We expose our reactive system to a certain set of reaction conditions and measure the corresponding energies and then correlate those energies with the stabilities of corresponding compounds, bearing in mind that we need to have the same reference points for all the compounds that we study. So what's the difference? Well, the difference lies really in the technicality. The heats of combustion are very large numbers. The huge amount of energy is released upon combusting organic molecules. On the other hand, heats of hydrogenation are not. They're relatively small numbers. And so what we end up facing is comparing two very large numbers which differ in a very small amount, or comparing two small numbers which differ in that small amount. It turns out that it's more accurate to compare two small numbers which have small difference than to compare two large numbers with small difference. And that's why for comparisons of alkenes, hydrogenation is really a method of choice, since we can get more accurate values that way than using heat of combustion. If we look how this actually works in practice, we can look at an example of 1-butene. And if this compound is hydrogenated, it will release minus 30.3 kilocalories per mole to get us to the normal butane. On the other hand, its isomer, trans 2-butene, can be subjected to the same reaction condition to give us minus 27.6 kilocalories. Since the value for trans 2-butene is lower, it means it's a more stable compound by the difference of 2.7 kilocalories per mole. And this indeed is a trend that we've already seen, that the tetra-substituted alkenes are more stable than tri, are more stable than di-substituted, and these are more stable than monosubstituted. And the explanation that is often invoked involves hyperconjugation, which basically stabilizes more substituted alkenes through the overlaps of their pi orbital with the neighboring sp3 orbitals of the alkyl groups. That overlap is absent, and the substituent is just a mere hydrogen because it's in a completely different plane. And so you see that hyperconjugation plays a role in instabilities of not just intermediate, such as cation and the radical, but also of stable molecules such as alkene. Now, what about cis-trans? What's the difference in stability between those two? Are they equally stable? Well, it turns out that they're not. So if we compare our cis-2 pentene, which is hydrogenated with release of minus 28.7 kilocalories per mole into just normal pentane, with its trans isomer, which is also hydrogenated but with slightly less amount of energy, we see that this trans isomer is more stable by about plus 1 kilocalorie per mole than its cis isomer. And the reason for this lies typically just in simple steric repulsion. There's a steric repulsion here, but there's very little of it here because the trans isomer formally is the anti-isomer. So there's very little repulsion. And you can expect that this difference would grow as the size of your alkyl groups starts growing and they start bumping into each other. Finally, cycloalkenes are more strained than even cycloalkanes. But it especially applies for small rings. The reason lies in the fact that the double bond, the sp2 carbons, would prefer the 120-degree rings. But the contraction of this bond angle in cyclic compounds is so severe that they really cannot get it. So if you have the cyclobutene, then delta hydrogenation is minus 30.7 kilocalories per mole in this molecule, whereas in cyclopentene, delta H hydrogenation is minus 26.6 kilocalories per mole. Okay? And this indicates again that the stability of this double bond is greater than the stability of this on account of lower ring strain. And one should also note that these numbers already abstracted the difference in stabilities of the rings because both of these compounds are converted into cycloalkanes, which presumably have the same amount of initial ring strain to begin with. Cyclopropene, of course, is very strained, but is still found in nature in certain carboxylic acids, which is pretty unusual. And one other issue which we should address is that of transalkenes. So this would be a cyclodecene, which is one of the first stable trans cycloalkenes. Normally cycloalkenes are not stable in the trans isomers because the twist in the ring is so high that they simply cannot close up the ring. The smallest cycloalkene that is reasonably stable would be trans-cyclooctene, which has 6 carbon atoms here, and closes up this. And if you look at the structure and construct the model, you will notice that this is a chiral structure, which is again one more example of molecules which have chiral structures without having chiral center. So this is an interesting side note. But basically, to sum up this little topic on stability of alkenes and cycloalkenes, the main method we use for them is the heat of hydrogenation, which allows us to draw comparisons with greater accuracy using heat of combustion, and we get to the trend that is supported by hyperconjugation. The tetrasubstituted alkenes are more stable than trisubstituted, more stable than disubstituted, and more stable than monosubstituted. And then between trans and cis, trans isomers are more stable. Cycloalkenes also have additional strain on account of the graded deformation of the ring angles from the 120 degrees. In the final topic of this lecture, we'll talk just briefly about the physical properties of alkenes.